All right. Welcome to the session on cryptography in the quantum era, I should say. This is a session where I'll be talking a little bit about some of the advancements in quantum compute and the impact that they have on cryptography as we know it. So the agenda in brief, I'll be talking about the advancements in quantum computing for starters. And then I will look at how that impacts cryptography, or what we call classical cryptography, and finally I'll go into a bit on what the post-quantum future looks like. So starting with quantum computing, we can separate the advancements in quantum technologies into two. So there's what we call quantum 1.0. Or quantum technology 1.0 and quantum technology 2.0. And what characterizes quantum technology 1.0 is that the capabilities we have as part of that were about, the quantum effects on an ensemble of particles such as photons and electrons. So we use that in things such as transistors and solar panels and so on. Now, with quantum technology 2.0, what we're actually looking at here is the exploitation of quantum effects on single particles, right? So things such as quantum superposition and quantum entanglement. And I'll go into all of that in a little bit more detail to explain what I mean by that. So when we talk about quantum technologies from a 2.0 perspective, there are a few interesting concepts that we have to think about. Now, the first is the idea of a qubit. Now, we're all familiar with a bit, like a binary digit, which is two states, 0 or 1. Now, in a quantum environment, when you have a qubit, it's actually a very interesting concept. Now, it is just like a bit in a digital world holds information, a qubit holds information in the quantum world. And one of the interesting properties of this is that we can put some of these particles, such as photons or electrons, in a state of what we call superposition. And when they're in a state of superposition, they are neither 1 nor 0, but they're actually a number of different states all at the same time, simultaneously having all of those states, which is it's a very interesting concept. I mean, it's a consequence of quantum mechanics, and it's hard to understand. But the point here is that when it's in superposition, it's in all of these states at once. And until the point at which you measure it, it does not take any specific form. Now, when you measure it, it'll collapse to either a 0 or a 1. But until it's measured, it's in all of these states at once. The third element that we exploit here from quantum mechanics is what we call entanglement. And this is what Einstein called spooky action at a distance, right? This is where you have two photons, for example, related in such a way that they share state. So, if the pair is in a state of superposition and it collapses to a certain state, both of these particles end up inheriting that state. So we exploit that in things like quantum computing, right? Now, quantum computing is really about taking those properties of quantum mechanics, such as superposition, interference, entanglement, and so on, to actually perform computations, right? And here's the key difference. When we have what we call classical computing, right? When you have bits, every bit is either 0 or 1, as I said. And so if you have 4 bits, then you've got 2 to the power of 4 possible combinations, right? And if you take these 4 bits, at any point in time, it can be one of those 16 values, right? Just one out of all those 16 values. When we talk about qubits, it's actually quite different. These bits are in a state of superposition. So the bits are both 0 and 1 at the same time. And you've got 4 bits, all of them 0 and 1 at the same time. That means that you have effectively all 16 values at the same time. So where you had previously needed 16 numbers to go through each of those different states, with quantum computing, you can have all of them at the same time. And this can result in an exponential increase in computing capability, right? Which we exploit in quantum computers. So the challenge here is that if we have a quantum computer that is powerful enough, and when we say powerful, we mean it's got a sufficient number of qubits, right? If it's powerful enough, then it could actually threaten some of the algorithms that we use for cryptography today. Now, such a computer is called a cryptographically relevant quantum computer, a CRQC, right? One that has sufficient capabilities. And we say that, hey, Q day will be the day when we have such a powerful quantum computer. We don't know when that's going to happen, and I'll come back to it. But if you have that, then our public key cryptography is at risk. That's the threat that we're dealing with today. And there are a number of exploitations of this. One of these is what we call harvest now, decrypt later attacks. So before I go into that, looking at a simple TLS handshake, right? In TLS, I've simplified this. The first phase, you're doing a key exchange using something like Diffie-Hellman, right, which is a asymmetric cryptography mechanism. You do authentication, and then you create a session key that is used for encryption of the data, right? So that's how it normally works. Now, what is happening, what we believe is happening out there is that bad actors, right, the bad guys are actually storing these exchanges for critical communication. They cannot decrypt it right now, okay? But they're storing it until a cryptographically relevant quantum computer is available. When that kind of compute is available, they can go back to this, replay all of that, and be able to decrypt the traffic, which is a bad thing, right? Now, not all data is going to be relevant at that point, but there is, the concept of shelf life of data. There could be some data that is very important, defense information, medical records, and so on, right? That have a long shelf life. So even if it's decrypted 10 years from now, it could still have an impact. So we need to protect that data, right? So how far along are we in terms of the quantum threat is the question. So the question, when is Q day happening? We don't really know, to be honest, right? There are many, many projections here, as you can see, and I'll skip through it pretty quickly. But the view is that when it happens, it will pose a great risk to the current algorithms, assuming that we are still using them. So the onus is on us to actually start building solutions to protect us against quantum compute. Now, some estimates show that we'll have a cryptographically relevant quantum computer by 2030. That's not very far away, right? So there's a whole lot of action happening around the world to deal with this. And just to give you some idea, in terms of capabilities today, if you look at the most powerful quantum computers, we're looking at about 1,000 qubits. That's not a lot. There are many, I guess, you could say approximations or estimates of the number of qubits required in order to break some of these algorithms. But they started like thousands of qubits. So while we're not there yet, it may not be too far. And you can see that there's been a whole lot of announcements on quantum compute chips coming out from the likes of Microsoft, from Google, and so on. IBM thinks that by 2033 we'll have large-scale quantum compute capability. So it's not far away, right? The threat is quite real. So what does that mean for cryptography? Which is the next thing I was going to go into. So I'll speed up because in the interest of time, right? Now, starting with symmetric cryptography. So with symmetric cryptography, the idea is very simple. We have a key, and that key is shared by two endpoints. The same key is used for encryption as well as decryption. So in this case here, Alice has some plain text that she wants to send to Bob. She uses the key, encrypts it, It becomes some sort of ciphertext, goes to Bob. Bob uses the same key, decrypts it, right? So everyone understands that this is pretty straightforward. The challenge with symmetric key algorithms is that, because of the nature of it, where we have to have the same key at both ends, it restricts its application. It's a more static application if you use it in isolation, because you have to have the same key at both ends. And so it doesn't scale to a very large number of endpoints, but it is very, very fast. The encryption is so fast, right? So we use it for bulk data encryption. And I think protocols such as AES and CHA-20 and so on are used for that. So for encrypting large amounts of data, we use that. The challenge is around key distribution. Now, let me just step back. In terms of key distribution, the predominant way of doing that in isolation is to use pre-shared keys, right? So you somehow agree between two parties. Maybe someone gives someone else a call and says, hey, this is your key. And that way you have the same key. It's a very manual process, pre-shared keys, right? But that's one way of doing it. It is used widely in the industry, okay? The other way is, that is emerging now, is called quantum key distribution. And this is actually a phenomenal way of doing it. It actually secures that key distribution channel using quantum mechanics. And this is the only key distribution mechanism that is provably secure, because any attempt to intercept it will be detected. So I'll touch on this a little bit more later. Now, the predominant way, though, of doing this is to combine asymmetric and symmetric encryption. So we use an asymmetric algorithm in order to encrypt the symmetric key. So that means that there's a very sort of close tie-in between symmetric and asymmetric, which could potentially cause us problems. So looking at it from a quantum perspective, right? There's an algorithm that was defined or that was devised by a guy called Love Grover, and this is actually called the quantum search algorithm. Basically, what it does is it reduces the time required in order to crack an algorithm or an algorithm such as AES. So where, from a brute force perspective, you would have needed an order n kind of operations to crack a key, this reduces it down to order square root of n, right? So it's a quadratic speed up, quite good, but it's still not enough, right? Because, it reduces it, but it doesn't reduce it to a level where it poses a real threat. So how do we deal with this when it comes to symmetric encryption? Very simple. If it's reducing it by square root of n, then all we have to do is double the size of the keys. So where we're using AES 128, use AES 2256. It's still pretty fast. For hashes, instead of SHA-256, use SHA-512. And so you're secured. So the bottom line is that symmetric key or symmetric cryptography is safe from quantum computer attacks. Now the challenge is with asymmetric, right? So with asymmetric, very briefly, you have two keys. You have a public key and a private key. So in this case here, both Alice and Bob have public and private keys. The idea is that the public key can be shared in the public domain, no problems, right? You can share the public key, keep the private key separate. Or not private key separate, but private key secure. So no one else knows it. And the way it works is, if you encrypt with the public key, you can decrypt with the private key. If you encrypt with the private key, you can decrypt with the public key, right? So they work interchangeably. So in this case here, this is used by a whole lot of protocols. TLS uses it, IPsec uses it, IPsec VPNs. And the algorithms, there's a few algorithms, right, that are associated with asymmetric encryption. There's RSA, there's Diffie-Hellman, there's elliptic curve cryptography. All of them are used here. So one of the applications of this, and I'll draw this up really quickly, is, as I said earlier, to distribute the key for symmetric applications. What we can do is take an example. Alice wants to send some data to Bob, and she wants to encrypt it using symmetric encryption. So she creates a key. It's called my secret AES key. And what she does is she actually encrypts it with Bob's public key. Now we know that once that's done, the only person that can decrypt it is Bob, right? Because that public and private key pair belongs to Bob. So he sends it to Bob, Bob decrypts it, gets it, very secure. There's other applications around signing as well, which I'll skip through. So this is really good because it's dynamic, right? You're doing it dynamically using things like, certificates and so on. So it can scale and it can use symmetric as well as asymmetric in conjunction. Now I'm gonna quickly go through this. The basic premise of all of these algorithms, RSA, Diffie-Hellman, elliptic curve cryptography, is that they work on what we call one-way mathematical functions. So it's very easy to perform that function, but very hard to reverse it. And one example that's used in RSA is, we pick two very, very large prime numbers, multiply them together. So P and Q, multiply them together, we get N. And what this algorithm is counting on is that there is no easy way, given N, to then derive P and Q. Now, this is a problem that's plagued mathematicians for the last 2 millennia. The problem of integer factorization. So given a number, to factorize it into its components. And the larger the number goes, the more difficult the problem. So there's no easy algorithm to solve this using classical compute, right? That's what we've relied on over all these years. So jumping ahead here, the challenge was actually accepted by this chap called Peter Shaw. So he said, hey, if I have a quantum computer, I can actually, really solve this factorization problem. And given what I described earlier about how, when you've got a certain number of qubits, you can use them in a state of superposition to have all of those states simultaneously active, right? That can be used in order to perform prime factorization. So it changed the entire basis on which RSA and Diffie-Hellman was based. So now if you have a sufficiently powerful quantum computer, all of that breaks. You'll be able to derive the private key from the public key. And that's obviously bad. So what do? Remember symmetric keys? We said just double the size and you're fine. You can't really do that with this. So we have to come up with a new set of algorithms that will be hard to crack by both classical compute and quantum compute. This is what we're calling post-quantum cryptography, right? There's a bunch of these algorithms, there's a desire to develop a bunch of these algorithms. Which leads me to the last point, which is the post-quantum future. So the way forward, as we said, in summary, symmetric key, nothing really changes. We do what we do today. Maybe beef up the size of the keys, right? Everything's good. Asymmetric cryptography, which is still needed, right? So no matter what you do, you need that in order to scale to something like the public internet and all the different applications out there. We have to develop new algorithms. And these algorithms fall under the umbrella of post-quantum cryptography. There's also quantum key distribution. In the interest of time, I will not go into this in a lot more detail, but reach out to me if you have any questions about it. But essentially, this is where we use a separate optical channel where we're sending photons that are in a state of superposition. And any attempt to eavesdrop here will result in that state of superposition collapsing, right? Which will be detected by the other end. So you know that if there is any eavesdropping here, it'll be picked up. So it's a very secure way of doing it. There are challenges though, right? If this was so great, we'd be using it everywhere. The challenges are you do need an optical channel, right? And there are limits to how far this can go. So this is spawning a lot of work around quantum networks in order to build larger and larger quantum networks where you can have not just point-to-point quantum key distribution, but more of a multi-point to multi-point, right? To build a network. It's a completely different field, a lot of interesting stuff happening there. Now, in terms of post-quantum cryptography, still based on mathematical algorithms, right? So there's a whole bunch of algorithms that were tested or selected by NIST, which is the National Institute of Standards and Technology in the US. And this is an open process. So if you're a mathematician and you've got a great algorithm, you're able to submit it to NIST. And then it's sent out in the public domain. People try and crack it. So a lot of these candidate solutions were submitted to NIST. In some cases, some of these supposedly secure algorithms were cracked within 24 hours, right? So that's the beauty of having it out in the public domain. You can really test it. But out of all of that, NIST have standardized 3 of them. As you can see there, that the part of FIPS 203, 204, 205. One's for key exchange, and the other 2 are for digital signatures. Now, these are algorithms. So you can think of them as equivalents to RSA and Diffie-Hellman and ECC and so on. Algorithms by themselves don't really do much, right? We've got to integrate them into the protocol infrastructure, into things like TLS and IPsec. So IETF is doing that right now. Some of the early work is ready, but there's still a lot of work happening in the space, right, to incorporate post-quantum algorithms. 3GPP is also looking at that as well. Now, it's going to take a long time for this to be incorporated into the internet infrastructure, right? I mean, everything uses encryption. Everything uses public key cryptography. So this is going to take a while for us to get there. Meanwhile, a lot of authorities around the world are getting worried about it. The World Economic Forum, there's the EU, the US has got some guidance on that. Singapore is building a quantum safe network, stuff happening in Korea as well. So, there's a level of urgency about this. And when you evaluating your strategy as an operator, then there's a theorem that we call it Moscow's theorem of cybersecurity. It's actually very simple, right? It's got 3 parameters. So X is the time you want to keep your system secure. Y is the time it's going to take you to deploy a quantum safe migration plan. And Z is the time it's going to take to build a large-scale quantum computer, which is kind of unknown, right? So you have to make some estimates there. And the idea is that if X plus Y is greater than Z, then you've got a period of exposure here, right? So the question is, what do you do? If you've got this exposure, what do you do? And there are many answers to this. But in general, we do what we know best, right? Which is to provide security, adopt a defense in depth strategy. So the area of weakness is around the application layer, right? The TLS, your SSH, your IPsec, and so on. And until we have, full PQC everywhere, there's going to be exposure there. So what you can do though is at the bottom layer, the transport layer, use symmetric encryption. Together with QKD or even whatever appreciate key strategies you have with sufficiently large keys, so that application layer traffic, which could potentially be decrypted, is now encrypted with another layer of symmetric encryption. So that provides you that extra security for that traffic until everything becomes PQC. Right. That brings me to the end of my presentation. Thank you very much. I'm not sure if we have time for questions. We have time for questions. Okay.
Yes, we have time for questions. So anyone have question to Paresh? So I may ask some question. So usually when we talk about quantum in the network, mostly we heard about the quantum encrypting or QKD or something. We mostly aware of how secure of the network instead of how to run a network. I know that quantum computing and quantum network is separate, right?
Yeah.
So and I would like to know if you have some insight from telecom provider, whether how the advance of quantum network in each provider or vendor about this one.
About a quantum network?
Yeah.
Look, I mean, there's a number of different quantum networks around the world, right? I mean, they're in research institutes and so on. So with quantum networks, it's a parallel activity, and it's all, like I said, it's all about addressing 2 things. One is the reach, because you're currently limited to a few tens of kilometers, maybe 100 kilometers if lucky, for quantum key distribution. So having a quantum network lets you go beyond that, right? So that's one thing that certain operators are working on. There's a lot of research happening there. The other one is that with a lot of the early implementations, it's all point-to-point QKD. So you cannot actually you can't really have multi-point communication. So with every pair of endpoints that are communicating, you need like separate optical links. So it's about having the ability to have a quantum network. That's exactly what a quantum network is doing, right? So that AE can have QKD comms with B and C and D using the same link, for example. And this is tricky because there are many ways of doing it, right? So the initial QKD systems were all about prepare and measure, where you're setting single photons and so on, right? Whereas some of the work that is being done with quantum networks is more around using entanglement and entanglement swapping and so on in order to build that. So yeah, look, I think it's still very much in its infancy. I think it's going to take a while before we get there. There's also free space QKD, right? With using satellites to do the same thing.
Okay, thank you. So that means QKD can still be coexist in the classical network, right?
Yes.
Okay.
Yes. Good. And QKD can coexist together with PQC as well. And we believe ultimately it's going to be depending on the security that you want for your data, right? QKD, as we said, is provably secure. Whereas PQC algorithms, they're still new, right? I mean, who knows? Like 3 years from now, someone might crack it. Whereas QKD will not suffer that.
Any more questions? If no, so thank you, Paresh, again.
Thank you very much.
Yes. Please give a hand to Paresh. Okay, thank you. So for our next speaker, we have the topics about IPv6, mostly experience at APRICOT from Yoshinobu Matsuzaki or Mas. So please welcome Mas on the stage. It's up to you. So if you
if I can use a common one, yeah, it's okay.
It's okay. Yep. Yeah. Come on. Got it. Go ahead.
So can I start? Right?
Yep.
Okay. So hi, this is Yoshinobu Matsuzaki. I'm working for IIJN, and also I'm leading the conference network for APRICOT. And at APRICOT, we use an IPv6 mostly technology to provide a connectivity for the conference attendee. So from that experience, I'd like to share what we found or lesson learned. So first, what's an IPv6 mostly? It's a new development and still under the standardization process. But basically, it provides an IPv4 connectivity on demand. If a client like our laptop or mobile phone really need to access an IPv4 world, the device or the network infrastructure automatically provide an IPv4 connectivity. But if they are happy with an IPv6 only environment, so the network looks like an IPv6 only. By this, we can estimate how much IPv4 demand is still on your network, right? Yes, we can do such a configuration by using the IPv6 v4 zero stack environment. It's easy, but still don't know when can we stop IPv4 or not. For sunsetting IPv4, we need such a technology and allow endpoint to use their latest protocol stack. And for that, we have two additional elements in the IPv4 v6 JORSOC network. First one is pref64 in router advertisement. Another one is IPv6 only preferred option for DHCP v4. by using those technology, we can provide IPv6 mostly network. So, client side, it's okay to use them without any additional configuration. So we need to set up router, and also if we have another DHCP server here, then yeah, you need to change that configuration as well to provide this option 108 IPv6 only preferred option. And also to send the NAT64 information, the router need to include that option in a router advertisement, IPv6 router advertisement. By this, the IPv6 mostly capable device, like Mac OS, if you're using the MacBook, then yes, it has a capability. Or iPhone and Android, they are all supported in IPv6 mostly. And if you are using Windows, still it's not capable to handle IPv6 mostly, but then we hope in the future, maybe Microsoft will change the mind to adopt IPv6 mostly. But then, as in our industry, some people are using Mac OS and iPhones, so they can use them and they can enjoy IPv6 mostly environment. So this is our configuration. So the red part of the configuration is for the IPv6 mostly related configuration. We use a Cisco iOS XE. It's an ASR 1K basically. We need to enable NAT64 to provide an IPv4 connectivity to IPv6 only client. Then we tell the needed prefix information to the client and include DNS option for the client in the array so that the client can resolve DNS hostname by using IPv6. And then some NAT64 configuration, it's a very common one. And this is another element, option 108. So basically, if your client support an IPv6 mostly environment, your client sending a 108 option to the DHCP server. And if our DHCP server understand 108 option, then the DHCP server returns, yes, we have a IPv6 only preferred network in this environment. So it's up to you, it's up to the client if you want to enjoy IPv6 mostly environment, or still if you want to use IPv4 on the native way, it's okay. So by telling that option, our server need to configure, yes, we are capable to handle v6 only preferred environment by conjunction with the NAT64. So this is the client behavior. So legacy side, like a Windows. So they can handle v6 and v4 natively, right? So it's an usual dual stack network. It gets an IPv6 address by checking the array, and also can use an DNS, IPv6 DNS resolver if inside an RDNS option in array. And also, as usual, it asks the DHCP server to assign IPv4 address, and in the DHCP offer, there could be a DNS option as well. So yeah, it's a common and a usual configuration. In the IPv6 mostly capable device, yes, it configures IPv6 address by using the array information. But yes, it asks a DHCP request with option 108, then receive a reply with an option 108. In that case, okay, this client understand this is an IPv6 mostly capable network. So doesn't need to configure IPv4. But then in case the client need to access V4 world, V4 internet, it use NAT64 to get an IPv4 servers or services. Because it can understand there is a NAT64 capable router in the network by receiving the array such an option, right? So it worked, but also we faced several problems. Let me share our experience. We observed a duplicate source IPv4 address. So macOS are using the same IPv4 address because it acts as a shared to use a NAT64. Right? It's a common address, 192.0.0.2 on the client side. It's a virtual address to access the V4 world from the V6 only network. Somehow, it shouldn't be leaked outside, but maybe this could be the bug of the macOS to send the multicast DNS service discovery and so on. So the macOS sometimes sending out an IPv4 packet to the network having the same source address. Doesn't that much problem, but then some smart wireless environment, it looks like a duplication, right? And in that case, some smart wireless environment refuse such a client to mitigate the impact of having the same source address. And in our environment, yes, we are using the Cisco WLC, and then the wireless network kicked out the client from the network. So we saw several clients having problem at the time. So we disabled the IP theft our use option in our wireless environment. Also, it's too smart. The wireless environment sometimes too smart. There is an option IPv4 DHCP required, enforcing your client to use a DHCP allocated address, right? In several attack scenario, client configure IP address manually to steal some information, but to prevent that, maybe the wireless controller has such kind of option. But then in the IPv6 only client, they don't need to ask DHCP for DHCP address, right? So looks like there's a client, but not properly asking V4 address. So somehow our wireless environment at that time kicked out such a client from the network. So we also needed to disable the option. Oh, and this is an NAT64 issue. Sometimes, not always, sometimes unnecessary IPv6 fragment header is attached to a packet. Don't know why. Could be a Cisco bug of ASL 1000 because we use that and we observed such a packet. Still, it can handle a packet at the destination, so it doesn't affect actual communication, but it looks strange. So we configure NAT64 setting fragment header disable option on the router, and this worked well to prevent such an unnecessary header attached to the packet. So here's some statistics. We observed almost 1,000 unique clients on the one day. So 88% used IPv6 mostly. And only 12% of our client still use dual stack environment. Don't know what's the ratio in your network, but in our conference, because we have more Mac OS users and iPhone users, that's why we see such a high ratio of IPv6 mostly user in our network. And traffic-wide, we observed 400 meg traffic. Yeah, it's common. So as I said, Apple, like a Mac OS, iPhone, iPad, they can handle IPv6 mostly, and Android, it can handle, and Windows 10 and 11, not yet. And if you are using the Linux, like Ubuntu or CentOS or whatever as your client, you can configure, but need to do it manually, not by default. But then still, if you have such a client in your network, you don't need to worry about that much, because the IPv6 mostly network works with such a client as well. Because for such a client, the network looks like a simple zero stack network. So it works. But maybe time by time, you have a more IPv6 mostly capable device in your network. Then at some point, you can stop the IPv4 service on your network. So IPv6 mostly is getting easier to deploy now. Your client already supporting most of it, I guess. And your routers, if you have not 6.4 capability, and if your DHCP server can handle 108 option, yes, you're ready to deploy IPv6 mostly. And if your wireless environment is too smart, be careful about such features. May bother with such an IPv6 only devices. And as I showed, you might face several issues during the deployment. Then please share such an experience so that we can handle or tackle such an issue together. Because we need to report such an issue to the developers, vendors, so that they can fix, they can aware, right? Okay, that's my talk. Any questions, suggestions?
Any question in the room? We have some room for 1 minute for question. Maybe I have one. So you know, like running V6 and V4 translation technique. So they have many hundred of things. So how do you think this implementation of 464 LAT is the like best practice? Prefer to DNS 6.4 or?
Yes, I think now most of the conference are now adopting IPv6 mostly by default, right? Because it's very handy and it actually works well.
Mm-hmm. Yep.
And then let your client use the latest protocol implementation. Mm-hmm. So yeah, it's one of the best practice among the conference network nowadays. And maybe you can implement in your enterprise networks as well.
Okay, thank you.
Thank you very much.
Thank you very much. Oh, we have another question. Can we? So he like say thank to you to sharing the information for us. Thank you. So please give a big hand for Mars. ขอบคุณครับ Okay, for the next speaker, the topic is BGP routing table update. We also have Dr. Philip Smith from NSRC. Please give a hand to Philip.
Not going to stand at the podium otherwise, anyway. So good, where are we? Almost afternoon. Yeah, so good afternoon, everyone. So I think some of you know I was doing a workshop for 4 days here, the BGP deployment workshop, just before the Beacon Experience Forum yesterday. I mean, one of the topics that we look at is really what the global BGP table looks like. You know, and it's really just trying to cover some of the good behavior practices, or what the industry expectations are, or whatever we want to call them. I suppose it's what we have been doing for many, many years in the global internet, just to try and make sure that it keeps working, making sure that the routers that we have can still manage the routing system, handle the 77,000 autonomous systems that we have in the global table. So I've been in the region since 1998, when I moved from the UK, when I joined Cisco, did the Cisco thing for 13 years, and then here I am now. But one of the things when I came to the region was that there wasn't really anybody looking at the global routing table. All that you really saw was the CIDR report, which Tony Bates had started in 1994 to encourage network operators to aggregate their routes when we moved from classful routing to classless routing. The only thing is, you know, by the time I joined Cisco, was people were using the CIDR report as kind of a league table of the world's biggest ISPs. When in fact it wasn't a league table of the world's biggest ISPs, it was a league table of the world's worst ISPs, as in with managing the routing system and what they were actually announcing. But it was kind of curious because most of the providers there were all from North America, and I was curious about what was happening in the Asia Pacific region. And so with APRICOT support, I mean, they hosted a small server and gave me access to the routers for the Brisbane office and also what they had in Japan. I just started looking at the routing table, but doing what the CIDR report did, but also looking on a per registry basis. So what was happening in the APRICOT region, because APRICOT were kind of curious, and I was kind of curious what was happening in Europe, because that's where I was from, because all you ever saw in the CIDR report were North American providers. So I don't know, I'm not going to go, I've given you a heap of information here. I've only got 20 minutes, so I'm just going to do highlights, and as I promised the workshop last 4 days, I'm going to have a look, see what's happening in Thailand, just for fun, because I was trying to show some of this during the workshop and I couldn't find the actual page. But anyway, so I've sorted all that out now. So there's a lot of info in here. So the BGP table, and this is the view at Dixie, which is the wide, I suppose, exchange point in Japan. So we're just about to hit 1 million v4 prefixes. So one of the other things I do is help with route views. I talked about that yesterday at the peering forum. And quite a few of the peers that route views has have already hit 1 million prefixes in the v4 BGP table. So I don't know, maybe in the next few weeks we'll get the, oh my gosh, you know, the fib can't handle more than 1 million prefixes. We don't know. We had that big kind of, well, flag day, I suppose it was, when we hit 500,000, because there were 2 router vendors, certain platforms were those, that only had a 512,000 fib entries burnt into hardware. So I wonder if we're going to have 1 million fib entries burnt into hardware for some vendor that we probably aren't aware about. I'm kind of curious to see. So, you know, 984,000. One of the things I do with my report, which I'll show you a bit later on, is I take the entire BGP table and aggregate it. Because obviously the ISPs that run the internet today are too lazy to do any aggregation. So I thought, well, if you guys are too lazy, what I'll do is I'll aggregate it. And if I do that, I can actually bring the routing table down to 380,000 prefixes. So if you quickly look at that, that's 600,000 prefixes in the global table today, which are useless. They are doing nothing whatsoever apart from being junk, total junk. So that's what's that about? That's getting on for 2/3 of the BGP table. It's rubbish. So if you think about it, you've got your car, you're driving around in your car. Do you keep your car back seats and boot full of rubbish when you drive around? I don't know, maybe some of you do, but I don't know, this is bewildering for me. And it's like, I wonder why the BGP table still works. There are lots of other things there. I'm not really going to wander through it, but in the Asia-Pacific region, so the region that APRICOT serves, there are about 260,000, and if we did aggregation, we could bring it down to 77. So that's actually even worse, right? That's way over. That's not even 2/3. It's substantially more than that. So, I don't know. People seem to enjoy it. So the worst deaggregator in the world is Amazon. They're announcing 13,000 prefixes. If they did some aggregation, we could bring it down to 5,000. Mobile net operator in Mexico, I have no idea what they're doing. They're trying to keep up with Amazon, but if they aggregate it, we'll come down, down to 582 prefixes. So you work out all these things. I have no idea what China Mobile has done. This only appeared a few days ago. They're announcing 11,101 prefixes, of which 11,000 are junk, because if they did some aggregation, it will go down to 101. A few people have noticed this, and it's like, and you can see it in some graphs, there's a jump of 11,000 prefixes in the V4 table. So I have no idea what China Mobile has done. This is Orange in Spain. Don't know what they're doing. TPG in Australia is a well-known junk announcer to the global internet. And so on goes down through the list. We've got Vietnam, various folks in the US, Telecom Indonesia has been there for years. Bharti Airtel has been there for years and years and years, and they've got an excuse every single time this is all pointed out. So this is the kind of prefix sizes. For V6, the V6 table is about 216,000. Biggest announcers, China Mobile likes being number one, don't they? So we're announcing 6,600. I haven't worked out the aggregation or deaggregation yet in V6. It's on my to-do list. I'll get round to it. I've been saying that for a few years, but I do want to work it out. It's almost as bad as V4. And what it's really showing is that the bad practices people are doing in V4, they're just replicating for V6. Problem with V6 is the address space is 128 bits. You don't have routers that can handle a deaggregated V6 internet if you behave the same way as you do for V4. And various random rubbish. This is always fun. So everything in green we see in the BGP table is IANA reserved. This should not appear in the global table. Yet, we see it here. Somebody just picks a number and makes it really big. It's all routable because people are not filtering ASNs. You should be filtering reserved ASNs. You should be filtering private ASNs. You should be filtering documentation ASNs. They should not be on the global table yet. In this view, they are there. This one, I'm baffled. It's a reserved ASN. Somehow they've created a ROA for it. How can you do that? I thought the registry interface to create ROAs didn't allow you to do that with private AS numbers. And it's in the global internet, and it's valid. So, in my humble opinion, that's just wrong. But I don't know. Maybe something has changed that I'm not aware of. Right? This ASN should not even be used for anything. Right? It's a reserved one. Private, I could almost understand. Reserved, not at all. No way. No way. Because it's not to be used. Somebody's decided to use documentation. I think they've just said 65536 onwards and upwards. I can just pick any old number I like. This one's funny. Do you notice this one? 2371355. I think they've got nervous finger over the digit 3. So they've added an extra 3 into the big AS path prepend. And there's another one at the bottom there. So that shouldn't appear there. They're doing it in V6 as well. So here's some, again, the nervous finger. added an extra, what did they add? A 5 at the end of what the AS number really is. So, yeah, we've got a couple of private ASNs, probably assuming that Cisco's removed private AS actually removes all private ASs, which it doesn't. What else? Deprecated. So AS-set is deprecated. Did you know that? It was deprecated in 2011. Still out there. And I think I saw a discussion somewhere that one of the BGP implementations is actually going to, if you get an AS-set, it's going to drop it. Well, it's deprecated. It should not be, we shouldn't be seeing anything that's using the AS-set. But they're still there. Lots of them in v4, even in v6. So if you're using AS-set or anything that produces an AS-set, please stop doing that. It's deprecated. Unassigned resources, these are all the AS numbers that are not assigned at all. Right? They're in the registry holdings, the 5 registries, but they're appearing in the BGP table. We've even got, you know, the private ASNs there, and we've got IANA reserved ones, all appearing. So, you know, that's the entire list. There's no registration information for these ASs. Anybody using the Internet Routing Registry to filter routes? Obviously not. Maz needs to come back and do another training on Internet Routing Registry because clearly nobody is paying any attention to it. So here we go. And it's not just dodgy providers who are announcing them. It's big names. Don't these people check anything? Oh, I know what they're doing. They're getting a letter of authority, that meaningless piece of paper that some ISPs still want. Right? RPKI is the way of authenticating this stuff. Letter of authority is not worth the paper it's written on, as Maz has said many times in several fora. So this stuff should not be appearing in the BGP table. v4 addresses, unassigned, but we'll announce them anyway. Who's stopping it? Aren't you meant to be doing that? Aren't you meant to be making sure the internet works? But we've got all this rubbish there. Prefix sizes, and I think I said in the workshop, the routing table is going to end up being all /24s for v4. It'll end up that. Really sorry, start buying your routers with big memory. And whatever bad things that people are doing in v4, they're doing in v6 as well. You can see the growth of /48s. We're over 100,000 /48s now. These have not been handed out by the registries. The growth onwards and upwards is kind of slowed down a little bit, but not too much. v6 table, onwards and upwards. Growth in ASs. Pandemic happened. The growth in ASs has slowed down. Right? It's kind of interesting just seeing that, how it's slowed down. It's fairly linear last few years. v6, no slowing down. This jump was APRICOT's assignment to a research project in China, 4,000 ASs and 4,000/32s. So suddenly they appeared in the global table a few years ago. That caused that one. Aggregation, you know, I calculate aggregation. I calculate the different v4 prefix sizes, you know. These aren't really growing anymore. It's the /24s that are growing. Where's the /24s? Oh, there we go. /24s carry on growing. So I say, the v4 table is all going to be 24s very soon. For v6, it's heading the way of being more than 50% /48s. How many 48s in a 32? You know, that's a lot. Growth in v4 address space size. The US military decided to announce all the /8s here because people were using them. And then, remember I mentioned China Mobile? Okay, what else? v4 AS announcements. v6 AS announcements, nothing too exciting there. Oh, the other fun thing that people like doing is AS path prepend. So in the early years of the internet, when we were all very responsible, we didn't have AS path prepends going crazy. Now we have, in the last 3 years, crazy, absolutely bonkers crazy. What does a 206 times prepend achieve? AS 131246, whoever you are. What does it achieve? Does it make it less important than a 2 times prepend? Well, of course it does, but why do you need to do 206? So it's bizarre. You know, they're the odd one here, and it'll be noticed on mailing lists, and people go, what on earth's going on? And they go, oops, fix it. Now, nobody cares. And they last for ages. You know, you look at some of the pre-pans, where is it? This one. This one was on NANOG discussed a long time. It was a Dutch provider who denied it was them, even though they were the email contact of the ones who was doing the pre-pan. V6, it's not getting any different in V6. The bad habits you do in V4, you do in V6. Look at it. 226 times pre-panned, 239 times pre-panned. I know which router you're using. Please don't use that router platform. It is garbage, right? Please don't. Implementation is broken. BGP is incomplete. Please do not use it. It belongs to a hobby room, not for running a commercial network, and definitely not on the internet, causing junk like this, right? Or learn how to use it before you connect it. Deaggregation in V4. So yeah, I mean, it's you know, the APRICOT region, it's actually slowly improving, right? The aggregation efforts. So that's pretty good, because certainly in the early years of the big growth in the internet in this part of the world, the deaggregation here was getting worse, mostly caused by China. But there's been a lot of effort in China to improve the aggregation. But for, who's orange? APRICOT region is just a mess. Latin America, this was the peak badness, and there's a lot of effort making improvements there as well. It's helped by better interconnects in South America, and just generally better behavior globally, but it's still a bit of a mess. If you look at North America, Europe, it's where it really should be. You know, 2 times deaggregation, 3 times deaggregation you can understand, because people need to do traffic engineering. But just taking your address block and chopping it as small as possible, that's not traffic engineering, that's just vandalism of the internet. So Asia Pacific region, so yeah, there's the China Mobile I talked about. So these are an APRICOT region, right, or the APRICOT member region. So what have I got, 3 minutes left? So a lot of Chinese providers, TPG of course, and then a lot of Australian, Indian providers as well. Those seem to be the 2 worst, and Vietnam, right? VTEL, VNPT, who else? Okay, I was looking at the list the other day. So those are the main issues. You know, I show the number of prefixes they're announcing. If we do aggregation, that's what we save. So that's what they're contributing unnecessarily to the BGP table. I mean, you can look at it and you say, oh, I don't really care, but you do care, because you have to buy the router that has to carry all these prefixes. They don't give you any extra routing information, but you know, they're there. Fun, Thailand. Here's the one I was trying to show the workshop. Okay, so these are the number of announcements being made. And if you aggregate, this is what it would actually end up being. So TOT, for example, announcing 1822, if they did aggregation, it would become 16. True, 720 could bring it down to 57. Who else is next? I don't know who SBN is. 599, 128. This one's a bit scary. 319 could come down to 7. So that's the top 20 list. Assumption University, 108 announcements, down to 3. You know, it's why? You know, you get an address block. Why do you announce it in lots of little pieces? So anyway, there's the list. It's in the slides. They'll be on the website. When I come back next year to ThaiNOG, please make that a little bit better. Then at least you can say Thailand knows how to run BGP better than anybody else does. It's not hard. THNIC, do the workshop. I'll teach it with other people. And BGP really isn't that difficult to try and do. But when you're doing this sort of announcing all this junk, when you really should be announcing that, you know, I don't know why. Address span, so this is just the amount of address space. So True has the most address space here in Thailand, followed by TOT. Triple T broadband also has, you know, this is just sorted in the amount of /20 equivalents that they have, just to give you an idea of the size. So size is not related to the deaggregation. So, observations. The growth we saw 2015 to 2020, so the pandemic really has slowed things down. V4 24 announcements are growing. What else? V6. Whatever you're doing in V4, you're just repeating in IPv6. I wish you would for deployment, but once you deploy it, you're just deaggregating the same mess as you do for V4. So anyway, I give this presentation every year. Nobody does anything about it or listens or makes any improvements. And they should. Anyway, questions over lunchtime so the next speaker can speak, I think. Anyway, hope it was useful.
Okay, thank you very much, Philip. So the last but not least, we have Thomas Corre. He will speak about container labs.
Hi everyone, my name is Thomas. I'm a product manager for IP routing at Nokia. And today I show you how you can build a digital twin, IP routing digital twin, with only open source tools at your disposal. Okay? Okay, let's get it on. Oh, the clicker. Sorry. Okay, so complexity. We operate more and more complex networks, whether you being an ISP, an Ethernet exchange point, or an enterprise. We used to have a lot of technical depth in our industry. We used to add things up and not remove things. So when you have things like merging service providers, networks, or you want to migrate from MPLS, an entire network from MPLS LDP to SRv6, or if you're an IXP, you want to move from TLDP-based VPLS to EVPN, those things are hard, right? Because it's a migration, it's a very big migration that you have to take into account, and you have to test it because the impact can be huge for your customers. So what do? You have to build a lab, right? So usually what I've seen most of the time, our customers, they buy 2 extra nodes, routers, or 4, and they test it in their lab, right? The problem with that, it's hardware is very good to simulate, to do stress tests, to do performance tests, to inject a lot of traffic, hundreds of gigabit. But the thing is, in terms of functional tests, you will not cover everything with 2 routers or 4 routers. You will miss things, you will overlook things, and you will just see them in production when it will fail. And that's we've seen a lot over the last years, honestly, with the service providers. So we need to do much better than that. And I'm not even talking about the lead times. You want to test something, it takes super long time to ship a hardware. You have to wire it, test it, change the setup, rewire differently. So it takes a long time. So what do we want to achieve? The dream, it's really about having a one-to-one copy of your production network that on which you could take your actions, do your test, revert back, do the merge, share with colleagues, try to different things. So for this, we know that the thing we need is a virtual lab. Okay? So not all type of virtual labs, in fact. What we want to have is a real digital twin. So I mean, same model simulated of your switch or routers, same version, same IP address, VLAN, everything like documented in production, not just something that you do, you try to do something on site, a real copy. And this is what we can achieve nowadays quite easily. I will show you. So here the demo is about using those tools at your disposal, which are free. There's a free version, an open source version for all those. So Netbox is your source of truth, your documentation source of truth. This is where everything is documented, right? This is quite popular, honestly, and this is not the niche thing or you know, a small tool. It's used in Cloudflare. They shared about it. It's used in DECX. It's used in many service providers. Then from there, you use NetReplica, or NRX for short. So NetReplica will do API calls to Netbox in order to generate a topology, okay? A virtual topology in a topology file. And what we will use is Container Lab. It was presented by a colleague before. Container Lab is an open source tool to simulate networks. NOKIA is the lead maintainers, okay, of this tool, and it aims to be the next generation of network simulators. So we build the lab with this topology created by NetReplica. And what we do then is we use a configuration management to deploy our configuration. So we use Python because this is one of the most flexible thing to do, but you could use Salt, Ansible, Narnia, everything that you are used to use. So what we have here for the demo is the representation of a data center, okay, small data center with a DC gateway on the top, which will be SROS-based Nokia. We have super spines here in the middle and attached to pods. We have 2 pods with the spine and leaf close architecture, okay? So inside those pods, we are running IBGP, and there is OSPF running on all the data centers. So you would say that's not the best design possible nowadays, but we will see that we will do some migration on this one, topology, and see how we can observe the changes and test in complete digital environment. So here is what happens on Netbox. This is an Netbox screen capture. So you have everything documented here. Each row is your one of your device, one of your router. You have the rack, the model, the name, the manufacturer, the role, the OS. You have tags, very important. We will see that we can use those tags, which is the metadata, to do some actions on it, and the IP addressing, VLANs, etc. Okay. So if you look in more detail on the specific model, here a super spine, you will see that you have the 2 first ports connected to your data center gateways, and the other ports here connected to your pods, the spines, and with all the IP addresses documented as it would be in production, okay? The /31's addresses. So the demo will be following those steps, okay? We will set up the environment, install NetReplica, which is Python-based installation, deploy Netbox, run NRX again Netbox to create the topology file, as I mentioned, deploy the topology with Container Lab, and then we will run the configuration script, Python script, to run the template and deploy what we want to achieve. So what we will do, because we need to simulate a change, right, a migration, and see how it works and if it's safe to do the similar way in production. So we will move from global OSPF here, initially, to completely removing it and putting in each pod an ISIS instance instead for better scaling, right? Better scalability. So you will have less churn, you will have less flood of information, and you will be able to scale better within your pods, okay? And you will have eBGP peering between your pods and super spines and DC gateway. So we can launch the video demo, and I will comment it for you. So you can clone this repo. It's available on GitHub publicly. and it will be based on those 5 bash scripts, small scripts that we use. So first we create the environment. So we need to install some packages for NetReplica and the configuration script. We will activate the environment. And then what we will do is that we will follow the steps, the 1 to 5. So we will install NRX, okay, which is a few Python scripts also. So it's there. We will install then Netbox, okay, which will be based on Docker Compose. So basically here we install and deploy Netbox along with everything documented as we've seen in the slides, okay? So it's already there. It's ready to consume. You have your inventory of DC gateway, spines, leaves. So here, once Netbox is installed and deployed, you can access the UI, okay? By default, admin, and you will see everything I've shared before, okay? You will see each node as a spine, represented as a leaf, as a super spine. As I've shared, you have the demo tag, you have the IP address, the software version. Everything is there. This is your intent, the source of truth. And this is the real representation of what's happening in a real network. Okay? So you have the interface here that are described and with addresses. So everything as expected here in this inventory. So what do we need to do from there? We need to run NetReplica. It will query Netbox, okay, via API calls, and those with the demo tag. Okay, there are a few nodes with the demo tag. It will put it in a topology file. We create a topology file. And this is the one. It's a YAML file with your nodes. So you have DC gateway. You have Graphite, which is for UI representation you can access. But your nodes, you have the DC gateway with the SROS version 23.10 exactly as described in Netbox. The model also, SR1S. You have your spines, you have your leaves with the correct model and version, and the links, so the interconnection between each device, okay? DC gateway to super spines, to leaves. So we have this topology file created like it would be in production. So now we can deploy this topology with Container Lab or CLAB deploy. So it just takes 1 or 2 minutes. It has been speeded up here. But basically, we will just use that file and generate the topology. So it's there. It's summarized in this table here. You have your DC gateway, super spines, spine and leaf. So here you can connect via SSH to one of the DC gateway here. This is what we've done. So you can check the version that it's correct as represented in Netbox. You can check the model. You can check the port. So it's 32 ports, 100 gig here. So here everything is down because there is no configuration, right? It's just the node represented in the inventory. We haven't pushed anything yet in terms of configuration. So we just have the basic config to do SSH, netconf, reachability, but nothing configured in terms of interface protocols. Here we connect to another spine, okay, which is based on SR Linux that you can see on the Nokia booth. So it's a D3L model, and you have also the version. You can check everything is in line with the inventory, the source of truth. So here by default, Container Lab is enabling the interface. Okay, so you have the interface up to connect to your spines, for instance, super spines and leaves, and you have LLDP running, so you can already see your neighbors here. You see the 2 leaves, you see the 2 super spine, because you are in the middle here, the spine. So okay, but no network instance, no protocols configured, nothing yet, like the DC gateway. So we need to push the config, right? And this is what we do with the Python script here that is there, configure.py, sorry. And so we will push the config on all those nodes which are in the topology. So what does it do? In fact, it's, as you can see here, sequentially pushing the config. And here you see the diffs, okay? So it's represented by some plus here on the right, left. And we are pushing the config as initially intended in the topology, the slide I've shared with you. So it will be OSPF, BGP on top running in the overlay, and all the interface configuration. So here it has been finished. So you see on each node those configurations have been pushed with the exact IP addresses as represented in your network. Okay. And the different parameters. So we can check on the DC gateway again to see the change after we've pushed the configuration. So what do we see here? We see the ports up and configured. It was not the case before. And we will also do some other checks. So we will look at OSPF. It's now there. You have your neighbors with the adjacency full, so it's established, and you have your BGP running with everything as described, the AES, etc. So here it's all there. So we will look at a spine then, which is a SR Linux based system, and here it's the same. You will see that the configuration has been applied. You have a default network instance. You have OSPF configured, as you see it here. And you could see also BGP. Sorry, the neighbors. You have all your neighbors, the super spines, the leaves, as intended. And then BGP, you see here, it's established. You have your pods and your super spine. So it's been a minute or two that it's running, right? You have some nodes here left, but they don't have demo tags, so they were not configured. This is what you use to deploy what you really want. So here, to test the change, okay, as we wanted, we take those nodes, in a pod. So the spines and the leaf. And what we will use in Netbox is a new tag that we will call ISIS equal initial. And what we will test for this change is to do something in seamless fashion, like make before break. So we will configure ISIS on top of what exists in the configuration. So the script, if we run it again, the configuration script, it will take into account that new tag, interpret it, and build the configuration which is required. So here you will see it will be mostly adding configuration, and it's ISIS configuration. Okay, so I add all my ISIS configs within my pod on my spine and leaves. And basically here I expect no hit, no traffic impact. Why? Because by default ISIS protocol preference is lower than OSPF. Okay, so you keep OSPF as the IGP. So this is what we'll see here. You see, you have your ISIS adjacency now. So this is configured. It has been pushed. And if you look at protocol preference here, OSPF is still active, true. ISIS false. So so far we haven't do any migration, right? It's just preparing the config to be there, to be ready to take over. And if you look at the BGP session uptime. We are about four minutes now. So look at it. This will be important just right after. So we've planned this, okay? So now we do the real migration that you could do overnight in production. Once it's tested and improved, you change the tag here. You put another tag, which is ISIS equals final. And what this will do, it will remove the OSPF config this time. So you can see the tag here in the documentation in Netbox. And again, applying this via Ansible or Salt, here it's the Python script which does the trick. We take this into account, this new tag, and we will apply configuration accordingly. So here you will see -diff, meaning that we are removing the config related to OSPF. So what are we doing here? We are switching the IGP. We are replacing OSPF with ISIS within the pod. So we have tested it at scale. You can see that we have already a few number of leaves. We could have 10, we could have 50. That would work the same. Here, ISIS adjacency is still there. Obviously, OSPF is gone. There is no output anymore. And if we look at BGP, right, you will see that it's still running. It's over 6 minutes now. So that means we've switched the IGP within a pod completely without interrupting the BGP session. No reset. So the overlay hasn't been touched, impacted by this change. So this is what we wanted to achieve, which is very good. And you have been able to test that potentially at scale with much more nodes as you would have in production environment, not just 2 box, right? Where you would see nothing. So here you see that ISIS is the active protocol for IP loopback reachability. Okay? So this is exactly what we wanted to achieve. So that was our change, our migration tested here. So I think we're good for the demo. We can switch back to the slide. And yeah, so if we just move one slide after, I think we're reaching the end. Well, yeah, okay. Thank you. So yeah, so as you've seen, we've created a digital twin with just open source tools that are very popular, that you can try yourself. You can copy this. We have many examples and multi-vendor examples. There is Arista, there is Cisco, there is Juniper. We also support Huawei VRPOS since a few months now. So, I mean, there's no excuse. You can try many things. Containerlab.dev, we have like 60 examples of networks that you can git clone. You can try yourself. So I really encourage you to take these tools as your new, more modern approach to work and collaborate and test. So, and also look at Netbox. It's a very good tool that you can use in a test environment and even for production. So any question, feel free to ask. And I see you later. Thank you.
Any question again? So, if not, thank you so much, Thomas.
Welcome.
Yeah. Let's give a hand to Thomas. Okay. So that's all for morning session.